We are Hell & Son Engineering, and this is our video presentation for the Peterson Gym pedestrian bridge. Hell & Son Engineering comprises 5 civil engineering students.
Erica Carino, Transportation.
Matthew Hellison, Geotech.
Gassan Schwede for Construction.
Jenny Mactodo.
And John Duya, Structural. New classrooms at Peterson Gym have increased pedestrian traffic and increased pedestrian vehicle interactions on 55th Street. This causes vehicles to stop more frequently and causes pedestrians to jaywalk or walk against red crosswalk signal. To solve this problem, Hell & Son Engineering designed a pedestrian bridge that allows grade separation to cross over to the classrooms at Peterson Gym and surrounding facilities without having to wait for traffic lights. So here's Gassan with the construction part.
Thanks, John. And today we're going to be talking first about the 3D model with the construction part, about the Peterson Bridge. It has 2 elevators and an 80-foot span, and it's 20 feet high. The construction plan consists of 6 phases. Phase 1 is mobilization and demolition, which will take about 20 days to get done. Mobilization is to move everybody in and do the site development and getting in and demoing part of the curb. The site phase 2 is a transportation evaluation, which consists of making sure traffic goes around with the correct signage and everything, and it is about 30 days of planning, about 30 days. Phase 3 is the foundation, which consists of the main structures underneath the bridge, just to hold up all the bridge, and it takes about 35 days to get done. The Phase 4 is the structural part, which is the major design part of the bridge, which includes the columns, slabs, and the stairs, along with the design of every single one of them, which consists about 160 days. And Phase 5 is the elevator installation, which takes about 60 days. The elevator consists of a pit, the elevator pit, which is a hydraulic elevator that goes up, and that goes for 3,000 pounds, that can hold up to 3,000 pounds of people. And the phase 6 is the closeout to clear up the whole area, and it's about 30 days to get done. So now we go on to the project schedule. The project start date is on October 1st, 2011, and it is a good starting date because it's in the halfway through the semester, in the fall semester, and there is about a month and a half to 2 months to get the students. They won't be on campus anymore for Christmas vacation. We will have about 1 year to do the completion and to go to the completion date, which is on November 31st, 2012. This project duration is about 365 calendar days, 241 working days. The working days include old working days that are Monday through Friday, not Saturday and Sunday, and if there are any holidays, they will be taken out. Then it's the project cost. It's the total cost of the project is about $1.1 million. It includes the materials, equipment, and labor, and general expenses. The materials, equipment, and labor are about $654,000, and general expenses is about $425,000. On this slide, we're going to be looking at the location of the bridge. I'm just going to hand it off to the transportation engineer, Erica Carino, to continue about it.
The bridge is located adjacent to the entrance of Peterson Gym and traverses 55th Street. Choosing a location was one challenge we faced. The bridge located here will maximize its utilization, be cost-effective, and maintain the integrity of surrounding buildings. Crossing to and from Peterson Gym in between classes occur in small groups, typically under 5 people. This number steadily increases prior to the start of a lecture, and when classes are dismissed, the highest concentration of pedestrians is observed. A pedestrian count is warranted from 10:45 to 11 on Wednesday, which is when the highest number of students is expected to be released from class. In this 15-minute interval, 438 students crossed and the crosswalk was triggered 19 times. At the bottom corner of the video, a student is cited for jaywalking. To accommodate for the bridge, the drop-off lane located in front of the Viejas Arena is augmented. A couple options were considered. It was decided to shorten the drop-off lane by 40.01 feet from the end closest to the bridge. This over the other option would maintain its aesthetics, be cost-effective, and maximize the workable space. The bridge, strategically constructed at this location, allows the removal of the crosswalk and traffic signals, reducing the number of stops vehicles have to make and serving high volumes of pedestrians. In place of the traffic signal is a stop sign serving the left turn movement coming out of the drop-off lane, directing drivers to stop before entering the intersection and give. Here's Matthew Hellison with the foundation design.
A cone penetration test, also known as CPT, was performed near the crosswalk of 55th Street adjacent to the Peterson Gym. Upon investigation of our data, we determined that it would be best to break down our soil into 8 different layers. Each layer was given a soil type and strength. Our overall soil profile starts with roughly 5 meters of clay. The top layer is 1 meter of overconsolidated crust. Below that, we have 20 meters of sand and gravelly sand. Then we hit bedrock at 25 meters. Our water table is located at 9 meters. However, due to the clay silt on the surface of our site, and for design purposes, we calculate the water table to be at ground surface. We came up with 3 options for our foundation design. Option 1 was a spread footing. This is our ideal option for the bridge based on cost efficiency and constructability. Our second option is a drilled pile. The pros of a drilled pile are it's more stable than a spread footing, you do not have to worry about liquefaction, and less noise than a driven pile. Our third option is a driven pile. The pros are it's more stable than a spread footing, you do not have to worry about liquefaction because it travels through multiple layers of soil, and it's quicker than drilled piles. It also eliminates the soil that would have to be hauled away if we drilled. Here's the bearing capacity calculations for our shallow foundation. We created an Excel file that included all assumptions and data collected from the CPT, and began to create a system to select the foundation's width based on the load applied to it. We know that the foundation has to support a load of 1,580 kilonewtons. Our assumptions are it would be a square footing, 2.75 meters, or 9 feet wide. The water table would be at the ground level, it would be fully embedded, and the top 2 layers would be excavated. We also assume that the self-weight of concrete is 25 kilonewtons per meter cubed. After running the calculations, we found out that the factor of safety for the drain condition is 3.7. Since we have created a shallow foundation that is embedded 4.5 meters, we decided that we should also calculate a deep foundation to compare cost. The deep foundation bearing capacity. It also has a load of 1,580 kilonewtons. Our assumptions are it will be driven, the water table is also at ground level, the width of the pile is 1/2 meter, the material is rough concrete, the self-weight of concrete is 25 kilonewtons per meter cubed, and we'd be using the beta method to calculate it. We came up with a pile that would be 15 meters deep and would give us a factor of safety of 3.6. Settlement for the shallow foundation. We are given that it is a square footing, it has a load of 1,580 kilonewtons, the water table is at ground level, it is fully embedded, and the width is 2.75 meters. After using Schmertmann's method, we found a settlement to be 7.3 millimeters. Now we will check that against the settlement of the pile foundation. The assumptions are based on the dimensions we used during the bearing capacity calculations. From these assumptions, we created this chart. Looking at the chart, we can see that with a load of 1,580 kilonewtons, a pile foundation will settle 5.4 millimeters. Since we found the shallow foundation to be as effective at holding the load as the pile foundation, we picked it as the foundation to implement based on the constructability and cost. Now we look at the structural design for our shallow foundation. We calculated a ultimate moment of 4,400 inch kips, which requires 8.7 square inches of steel. We checked that against the steel provided, and we found that we can use 12 number 8 bars, giving us an area of steel of 9.42 inches squared. Next, we had to check to make sure we had enough development length. After running the calculations, we found that we needed 28 inches to have adequate development length. Our foundation provides 42 inches. That concludes the foundation design. Here's Jenny with the structural design for our bridge.
Before beginning the structural design of our pedestrian bridge, we first had to take into account many of the criteria and constraints that we had. First was the height clearance of the bridge. From AASHTO LRFD bridge design specifications, they require a height clearance of at least 17.5 feet from the road. We chose a clearance of 20 feet just to stay conservative. Next was the span of the bridge. Because it'll be crossing over 55th Street, the span of the walkway will need to be at least 60 feet. We chose an 80-foot span of the walkway in order to accommodate for the columns of the bridge without constructing on top of the sidewalk. We also had to consider the width of the walkway. It will have to accommodate the flow of foot traffic of pedestrians who will utilize the bridge. After obtaining data of pedestrian counts and the volumes of students with classes in Peterson Gym, we decided that a 12-foot width will accommodate a comfortable walking area for each individual. We were also restricted to the measured area of our location. Because of the surrounding buildings, we were heavily restricted in terms of how much area we would have for the bridge. We also have to consider access to individuals with disabilities. In order to allow grade separation to and from Peterson Gym, stairs will be designed alongside the bridge. However, because the bridge is constructed for public use, it must be readily accessible to and usable by individuals with disabilities according to the ADA standards for accessible design. We first considered a bridge with ramps. However, handicap ramps would have a required 20-foot minimum span for every foot of vertical rise. Because the location of our bridge does not accommodate enough space for handicap ramps, we decided that elevators would be a better option. And lastly, of course, is aesthetics. Because it is placed in a location where many students and visitors will be entering campus, it should be pleasing to the eye as well as reflect San Diego State University. We took into account several possibilities for the bridge design. Different bridge types include beam bridges, cantilever bridges, arch bridges, suspension bridges, and cable-stayed bridges. Because our bridge will have such a short span of 80 feet, we decided that a simply supported frame beam bridge will be sufficient. Now here is John with the walkway and column specifications.
The walkway makes use of a box girder design. The calculated dead load, which includes the self-weight of the box girder plus the weight of the concrete barrier, is 4.9 kip feet. The live load, which accounts for the loading imposed on the pedestrians, is 1.08 feet. The factored loading, 8.71 kip feet, is calculated loading from both dead and live. This loading is used for design. The calculated deflection of the bridge from the loadings is 0.29 inches. Concrete acts well in compression but fails in tension. To ensure that the bridge does not fail in tension, steel reinforcement is needed. Based on the calculations that are further explained in our project report, we used 30 number 11 steel reinforcement bars. Here is an AutoCAD draft of the box girder. The main column makes use of a square tie design. The columns need to be designed to handle loading from the walkway. The calculated loading from the walkway is 4,181 kips. We designed a column area of 30 by 30 inch with 8 number 10 steel bars. To ensure that the column will handle the loading, the equation shown below calculates the bearing capacity. Here is the table that we use to calculate for shear reinforcement. Since the shear max is greater than 72 kips, stirrups are required. However, the max shear is not greater than 431 kips. Therefore, stirrup spacing for shear reinforcement will be equal throughout the span of the walkway. Stirrups will be spaced evenly at 12 inches apart. This concludes the video for Hell & Son Engineering Senior Design Report, the Peterson Gym Pedestrian Bridge.